Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 9th, 2025, just 2 days ago. The standout result is a topology-aware dynamic Gaussian method, TaoGS, that renders high-fidelity volumetric videos while staying highly compressible, achieving up to 40 times compression with strong image quality. The paper is titled, Topology-Aware Optimization of Gaussian Primitives for Human-Centric Volumetric Videos. And as we will see later, the implications for volumetric capture and streaming are quite significant. The method cleanly separates motion from appearance, adapts to clothing changes and object interactions, and supports fast training with real-time rendering. On X, a post highlights topology-aware Gaussians that track long motions and render high fidelity despite topological changes, with a short demo video and solid engagement around 120 likes. The previous segment summarized the headline results and the social buzz. Figure 1 presents a visual teaser that illustrates long motions and topology changes, because the performer moves from sword handling to umbrella interaction, while clothing and pose evolve. The left series shows dynamic sword draws with clear reflections, which emphasize temporal coherence. The right series highlights umbrella unfolding and flowing garments, signaling object interaction and changing geometry. Together, these scenes convey high-fidelity rendering that stays stable across significant motion and appearance shifts. The previous figure set the stage with teaser visuals. Figure 2 lays out the full pipeline, which starts with an 81 camera capture that feeds an input data stream into an optimization stage for sparse motion Gaussians. Candidate filtering uses a spatio-temporal tracker and error maps, so newly observed topology gets added while bad points are rejected. Graph updates maintain an as rigid as possible deformation structure that stabilizes motion. A Gaussian lookup table then maps motion to activatable appearance Gaussians, and the attributes pack into two-dimensional maps for codec-friendly H.264 output. The previous figure outlined the pipeline. Figure 4 presents a qualitative comparison across methods, showing two challenging scenes with clothing motion and thin object interaction. The columns align ground truth, several dynamic Gaussian baselines, and our method, while circular zoom insets emphasize textures and edges that tend to blur. The comparison highlights sharper logos, clearer sleeve folds, and more stable thin strands, which indicate better temporal coherence and topology handling. The visual gains matter, because crisp details confirm accurate motion tracking without over-smoothing. Alright, the previous figure showed visual quality, and Table 2 now quantifies speed and storage across methods. The table reports storage per frame, training time per frame, and rendering frames per second, which together indicate practicality for capture and playback. TaoGS stores the least at 0.411 megabytes per frame, while after compression, ours reaches 1.335, with far higher fidelity retained. Training takes 108 seconds per frame for ours, and rendering hits 125 frames per second before compression, so real-time playback is achievable. Alright. The previous table focused on speed and storage, and Table 1 now reports rendering quality across methods. The table lists PSNR, SSIM, and LPIPS, which measure fidelity and perceptual similarity, so higher PSNR and SSIM and lower LPIPS indicate better results. Ours before compression leads with 37.264 PSNR, 0.9911 SSIM, and 0.0182 LPI pages S. After compression, quality stays strong with only a small drop. Wrapping up, two takeaways stand out. TaoGS cleanly separates motion from appearance, which enables robust tracking through clothing changes and object interactions, and it packs attributes into lifespan-aware, two-dimensional maps for up to 40 times compression with minimal quality loss. The broader implication is practical, high-fidelity volumetric streaming. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.